The problem. We are given the open-loop transfer function g sub o of s equals k times s squared plus 4 divided by s plus 3 times s minus 1. K is a free gain. The system is in a unity feedback loop, so we ask 3 questions about the closed loop. Question A. Sketch the root locus and write down the rules used. Question B. For which values of k is the closed loop stable? Question C. For which values of k is the closed loop oscillatory? Notice the open loop characteristics already make this interesting. Open loop poles, -3 and +1. The pole at +1 is in the right half plane. The open loop is unstable. We want feedback to fix that. Open loop zeros. Solve s squared plus 4 equals 0. S equals plus or minus 2j. Pure imaginary zeros sitting on the j omega axis. 2 open loop poles, 2 open loop zeros. N equals m equals 2. The strategy. 3 questions, but they all live on the same closed loop characteristic equation. Build it once, then read 3 different facts off of it. Step 1. Write the closed loop characteristic equation. 1 plus g sub o of s equals 0 expanded. The result is a quadratic in S with k-dependent coefficients. Step 2. Stability. The CE is second order. Apply the necessary condition for a quadratic, every coefficient strictly positive. Get a k range. Step 3. Oscillation. A second-order system oscillates when its roots are complex, which happens when the discriminant is negative. Compute the discriminant and find where it goes negative. Step 4. Root locus. Use the standard rules, real axis segments, asymptotes, j omega axis crossing, to sketch the path of the closed-loop poles as k varies from 0 to infinity. 3 questions, 1 characteristic polynomial, 4 short calculations. Let us begin. Step 1. Closed loop characteristic equation. Set 1 plus g sub o of s equal to 0. 1 plus k times s squared plus 4 all over s plus 3 times s minus 1 equals 0. Multiply through by the denominator. S plus 3 times s minus 1 plus k times s squared plus 4 equals 0. Expand the first product. S plus 3 times s minus 1 is s squared minus s plus 3s minus 3, which simplifies to s squared plus 2s minus 3. Add the k-weighted 0 polynomial. Ks squared plus 4k. Collect by power of s. Coefficient of s squared, 1 plus k. Coefficient of s, 2. Constant, minus 3 plus 4k or 4k minus 3. The closed-loop characteristic equation is 1 plus k times s squared plus 2s plus 4k minus 3 equals 0. 3 coefficients, 2 of them carry k. This single quadratic is the key. We will mine 3 different facts from it. Step 2. Stability. The characteristic equation is a quadratic. as squared plus bs plus c equals 0, with a equals 1 plus k, b equals 2, and c equals 4k minus 3. For a quadratic, stability has a clean shortcut. The system is stable if and only if every coefficient is strictly positive. This is the Routh-Hurwitz necessary condition, which is also sufficient at order 2. Walk through the 3 coefficients. A, positive, 1 plus k greater than 0, gives k greater than minus 1. B, positive, 2 greater than 0, always true, no constraint on k. C, positive, 4k minus 3 greater than 0, gives k greater than 3/4. Combine. The first inequality demands k greater than -1. The third demands k greater than 3/4. 3/4 is the tighter bound, so it dominates. Stability range. K must be strictly greater than 3/4. At k equals 3/4 exactly, the constant term vanishes. One root sits at the origin, marginally unstable. Below 3/4, stability is lost. Answer to question B. Closed loop is stable for k greater than 3/4. Step 3. Oscillation. A second-order system oscillates when its closed-loop poles are complex. A complex conjugate pair gives a damped or undamped sinusoid in the time response. Real poles give a sum of decaying exponentials, no oscillation. The two roots of a s squared plus bs plus c equals 0 are complex when the discriminant is negative. Discriminant equals b squared minus 4ac. Plug in. B squared is 4. 4ac is 4 times 1 plus k times 4k minus 3. Expand the 4ac term. 4 times 1 plus k times 4k minus 3 equals 4 times, opening the bracket, 4k plus 4k squared minus 3 minus 3k. Group. 4 times 4k squared plus k minus 3. So 4ac equals 16k squared plus 4k minus 12. Discriminant. 4 minus the bracket. 4 minus 16k squared minus 4k plus 12, which is 16 minus 16k squared minus 4k. We need the discriminant strictly negative. 16 minus 16k squared minus 4k less than 0. Multiply by -1 and flip. 16k squared plus 4k minus 16 greater than 0. Divide by 4. 4k squared plus k minus 4 greater than 0. Solve the quadratic in k. K equals -1 plus or minus root 1 plus 64 all over 8. Root 65 is approximately 8.06, so the two roots are approximately 0.883 and -1.133. The quadratic in k opens upward, so it is positive outside the roots. K less than -1.133 or k greater than 0.883. Combine with stability, k greater than 3/4, that is, k greater than 0.75. The stability range starts at 0.75. The oscillation range starts at 0.883. The intersection is k greater than 0.883. Answer to question C. Closed loop is oscillatory when k is greater than approximately 0.883. The exact value is root 65 minus 1 all over 8. Between 0.75 and 0.883, the system is stable but not oscillatory. Two real negative poles. Step 4. Root locus. Now sketch where the closed-loop poles travel as k varies from 0 to infinity based on the rules of root locus construction. Rule 1. Number of branches. The locus has max of n and m branches. Here n equals m equals 2, 2 open-loop poles, 2 open-loop zeros, 2 branches. Rule 2. Start and end. Branches start at the open-loop poles when k equals 0. Branches end at the open-loop zeros when k goes to infinity. With n equals m, every branch lands on a finite zero. No branches escape to infinity. Rule 3. Real axis segments. A point on the real axis lies on the locus if and only if the total number of open-loop poles plus zeros to its right is odd. Real poles are at -3 and +1. Real zeros, none, since the zeros are at plus or -2j. Test the segment between the real poles. To the right of any point in this segment sits one open-loop pole, the one at +1. Count is 1, odd. So this segment is on the locus. Test to the right of +1. 0 open loop poles or zeros to the right. 0 is even, not on locus. Test to the left of -3. 2 open loop poles to the right. Even, not on locus. Conclusion. The real axis portion of the locus is the segment from -3 to +1. Rule 4. Asymptotes. With n minus m equals 0, there are no asymptotes. Every branch terminates at a finite 0. Rule 5. J omega axis crossing. Substitute S equals J omega into the characteristic equation and solve for real k. Real part -1 plus k times omega squared plus 4k minus 3 equals 0. Imaginary part 2 omega equals 0, so omega equals 0. The locus crosses the imaginary axis only at the origin. Plug omega equals 0 into the real part, 4k minus 3 equals 0, gives k equals 3/4. The crossing happens exactly at the stability boundary, consistent with question B. The picture. 2 branches start at -3 and +1 on the real axis when k is 0. As k grows, they slide along the segment toward each other, meet, then break away into the complex plane and curve upward and downward, finally landing on the zeros at plus and -2j as k goes to infinity. The locus crosses the j omega axis at the origin when k equals 3/4. That is the moment the closed loop becomes stable. The breakaway from the real axis happens at k equal to √65 minus 1 over 8, about 0.883, the moment oscillation begins. Summary. Open loop transfer function. G sub O of S equals k times s squared plus 4 divided by s plus 3 times s minus 1. Open loop poles at -3 and +1. Open loop zeros at plus and -2j. N equals m equals 2. Closed loop characteristic equation. 1 plus k times s squared plus 2s plus 4k minus 3 equals 0. 3 answers. Question A. Root locus. 2 branches starting at the real poles -3 and +1, sliding along the real axis segment between them, breaking away at k equal to √65 minus 1 over 8, curving into the complex plane and ending on the zeros at plus and -2j as k grows large. The locus crosses the j omega axis at the origin when k equals 3/4. Question B. Closed loop is stable when k is greater than 3/4. Question C. Closed loop is oscillatory when k is greater than √65 minus 1 over 8, approximately 0.883. Big picture. 3 questions, 1 characteristic equation, 4 short calculations. The closed loop poles tell every story: stability, oscillation, transient shape, and the root locus is the picture that binds them together as a function of the gain. This concludes the midterm worked example series. 20 problems covering plant modeling, transfer functions, state space, linearization, stability, time specs, and root locus.